hand it to Patrick, and we will have the first keynote by Craig. So Patrick.
Okay, well, welcome. Good afternoon, morning, appropriate global time zone to everyone joining this conference session. It's my great pleasure and good fortune to introduce Dr. Craig Sherstan and his keynote lecture on an important breakthrough in RL and games, GT Sophy. Craig today is going to share how he and the team at Sony AI work to build an AI racing agent that's not just competitive, but also fun to play against for individuals of all levels. As a sidebar, I have raced against various Sophy agents and completely lost. I am not a great GT driver. My training in Mario Kart did not translate very well. Craig's talk will be roughly 45 minutes in length. Please place your questions in the meeting chat. I will moderate a Q&A based on your curiosities after the talk concludes. But again, I'll say we are so fortunate to have Dr. Sherstan here with us today. I've known Craig for well over a decade as a graduate supervisor and friend, and I've had the great privilege to collaborate with him actively over the time we've known each other. His research contributions have spanned everything from fundamental artificial intelligence to the conductivity of gold-structured nanofilms, to robotics, intelligent bionic limbs, to encoding sportsmanship as reward functions for game-playing agents. I primarily think of Craig as a top-tier research scientist specializing in reinforcement learning, settings where agents learn how to behave by interacting with their world. As a Vanier scholar, Craig's graduate research focused on developing agents that construct predictive models of the world through experience and that set the foundation and the stage for some of the exciting innovations that followed, including what we'll hear today. Craig is no stranger to sharing his research widely. His first authored or co-authored research has been published at top venues, including IROS, NeurIPS, AAAI, and the journal Nature. He's also a startup founder, has had a sustained career in software development, has had roles in project management, team leadership, and business development. But my strongest impression of Craig is that he's a person committed to making the world a better place through software, science, or hard on-the-ground volunteer work in places around the globe that need it most. He's demonstrated again and again his commitment to solving real-world problems whose solutions can fundamentally improve our society, and that includes games. Please join me in welcoming Dr. Craig Sherstan to the virtual stage.
All right, thanks, Patrick. All right, everyone. Today I'm going to talk to you about GT Sophy. This is an AI agent that we here at Sony AI created to play the game Gran Turismo. And we have both made it superhuman, and now we are working on making it fun for everyone to play. To get started, I'm going to let this trailer introduce the project.
Sorry, Craig, you need to share your screen first.
Sorry about that.
Yes, I was just going to note, Craig. It's
kind of key, isn't it? All right, let's start that one more time.
There's very few places where you can go out and say, I'm going to build an AI, and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo with Sophy is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
この車文化、車という存在をもう丸ごとビデオゲームの中に再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophy agent?
This is not just a technical breakthrough project, but it really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースしていきたいなっていうふうに思いましたね。
that gives you an idea of what we're going to be talking about today. So I am just one of many of the people who contributed to this project. As you can see here, lots of collaborators. So let's talk first about Sony AI. Sony AI was established in April of 2020. We have a remote workforce in North America, and we have offices in Tokyo, Zurich, and Barcelona. We have 6 main areas of research, including gaming and interactive agents, which is a group that I'm a part of. We have a group for AI for creators. We look at scientific discovery, imaging and sensing, robotics, and we have a core team focused on AI ethics, which has been really influential both at the global political level and within Sony as well. This project was a partnership between 3 groups: Sony AI, Polyphony Digital, which is the game maker for Gran Turismo, and Sony Interactive Entertainment. So for those of you who aren't familiar with Gran Turismo, it is billed as a racing simulator. So this is not Mario Kart. There's really a focus on high fidelity simulation. It's been around for over 25 years in the PlayStation ecosystem. Here I'm showing you video of in-game images on the top, and then real-life video from a racer, Ken Chan. And one thing that's really interesting about this video is that Ken went out and he tuned his car the same way in the game and for the track. And then he went out and collected lap times, and he was able to get lap times within 0.1 seconds between simulation and the real world. Just kind of commenting again on the fidelity of the game. Many of you have probably seen the movie Gran Turismo. This is a movie that chronicles the real-life story of Jan Mardenborough, who was part of this program where they took Gran Turismo players and trained them to race real racing cars. So the problem that we were handed is that existing AI drivers for these video games are really, they're slow, they're boring, they're non-responsive, they're predictable. And essentially, once players reach a certain level of competence in these games, these built-in AIs are no longer competitive for them. They no longer give them a challenge, no longer give them an opportunity to continue learning. Okay, and our solution was to train an agent using reinforcement learning that could outrace the top human players. I want to pause on that for a second. So we're at this time in history where we're debating, where's the role of AI, and concerned about AI replacing humans in many things. This I really like. This is a problem that humans couldn't solve using traditional approaches, and this is an opportunity where we were able to bring in an AI system to solve an previously unsolved problem. Let's talk a little bit about the timeline of the project. It started in 2016. As an internship project inside of Sony. This was Florian Fuchs who started this project. And then in 2020, a startup called Kochitai was acquired, came Sony AI, and this project was incorporated. We were gearing up to race against the top humans, and in 2021, we had our first event where the humans won. And then in October of that same year, we came back and won against the humans. That led to a publication in February in Nature, and then further to, since then, we've been working on getting Sophy into production and making it available for everyone to play against. Okay, so the event was structured as follows. We had 3 courses, 3 different tracks. For each course, a different car was selected. We let the human drivers know ahead of time which courses and cars they were going to be racing on. And these were drivers that were selected. They're some of the top drivers in the world at Gran Turismo. During this time, this was during COVID, we were limited, unfortunately, to getting essentially the top drivers in Japan. All of these guys are world-class drivers, though. Scoring was done as a team. So we had it was 4 versus 4. So 4 of our GT Sophy agents versus 4 humans. Scoring was done based on the final position when they crossed in the finish line at the final lap. And the SART, this one here, SART, was scored at double the points. It's a very difficult track with a very difficult car to drive. So in July 2021, we had our first race and we lost. It was fairly close, but we lost. And I'm going to talk about one of the reasons is that there was a difference in expectations. So when we were building Sophy, we had made this assumption that every car out there was a competitor. That's the way Sophy sees the world. And that the goal was for every car out there to achieve the best possible position that it could. Okay, and yet we set up the event as essentially as a team event. So for humans, for Sophies, and the humans treated it as a team event, and they worked together to block out Sophy to make sure that Sophy couldn't gain positions. Okay, so that was obviously a bit of a discrepancy, and certainly one of the reasons why we lost that event, not the only one. We learned some things from that event. Some technical things, and one of them, and we came back and made some changes. So we changed our network architecture and really focused on identifying situations where Sophy had not performed well in the races and ensuring that we had training scenarios that handled those specific cases. In October of 2021, we came back, we had a new match, and we won. And one of the key things at this time was, of course, the training, the changes, training that I mentioned, but also communicating with the humans clearly that they were expected to drive to the best of their individual ability and try to achieve the top position that they could get. So with these changes, we came back and we won by a significant margin. This led to publication in Nature in February 2022, sorry. And a year later, we had a limited beta test where Sophy was released into the GT ecosystem for 1 month. So this allowed real-world players, not just the best, to play against Sophy in a limited fashion. We learned from that experience, and since then we've been working on getting GT Sophy into the game, and as of November of 2023, Sophy is now a permanent part of the game. So you can play it in Gran Turismo 7 on the PlayStation 5. Unfortunately, it's not available on PlayStation 4. Players can now race with our agent on up to 13 tracks, and Sophy can drive over 400 cars. So that kind of covers what we did. Let's talk about how we did it. So as I mentioned in the beginning, we trained Sophy using reinforcement learning. And in reinforcement learning, we have our AI agent, in this case, Sophy, that interacts with its environment, in this case, Gran Turismo. On each time step, Sophy receives an observation of the world. It converts that to a state representation. And based on that input, it takes some action. The environment changes. Sophy gets a new state observation and also a reward that says how good the action it took was. And Sophy's job is therefore to learn policy that maximizes the amount of total return that it'll receive over the course of a race. I'm not going to go into a lot of technical details, but just really high level, we used soft actor critic. This is a policy gradient method that has two main components. One is the policy, which is the thing we really care about, that learns our mapping from state to action. The other one is our value function, and this is given a state and action, estimate how good it was to take that action in that state, and then follow our policy. And this is used for training the policy to provide a signal to train that policy. We ended up using a modification of this called quantile regression SAC, where instead of our value function just predicting, say, the mean or the expectation, it predicts the distribution of the returns. And we found that empirically, this produced better results. Lower lap times is what I'm showing here. So nearly a whole second difference in average lap time. We also found that end-step returns were beneficial for improving performance. And overall, we had a very simple model architecture with 4 layers, 4 fully connected layers, each with 2048 nodes and ReLU activation. So when we started this project, one of the first things we had to do was to build cloud infrastructure for training Sophy. We partnered with Sony Interactive Entertainment to do that. And what we have now today is a cloud infrastructure that lets us train directly on PlayStations. So we can send policies to the PlayStations. Those are rolled out. We collect data. That data goes back to another process with an experience replay buffer. And our trainer process, which has a GPU, is then used to update the policy and queue functions. Let's talk about Sophy's observation space. Sophy sees essentially itself, proprioceptive information about itself, including velocity, acceleration, roll, pitch, and yaw, and wheel loading. And it also sees what we call tire slip. So this is the difference between the direction that the car is moving and the direction that the tires are pointing. And Sophy sees a projection of the course in front of it. So we do this by projecting points along 3 lines, left, center, right. They are velocity based, meaning that the distance between each point is based on the speed that Sophy's traveling. So as Sophy comes into this corner and starts slowing down, the distance between those points is getting smaller. And then as Sophy begins to accelerate out of the corner, we'll see the distance begin to expand. Sophy's action space is pretty simple. Our network output has only 2 heads. It has one that maps to braking, acceleration, and for reverse, which is needed if Sophy has an accident. And then we also have another head for steering. These operate all at 10 Hertz. All right, so this is enough to get us to the point that we can drive around the track by ourselves, which we'll call time trial, and record times and go really, really fast. So I'm showing here a video of Sophy just taking this Maggiore course, and you can just see how closely it gets to the walls and these kind of things, just really accurately taking the optimal line through this course. And we can get, within 24 hours of training, we can get our times down to top human performance. And when we look at where GT Sophy makes up time, it, of course, is in the corners, in these some really complicated corners on the tracks. Okay, so we talked briefly about time trial now, but our goal was to play against other humans. And so we'll talk about how we train with opponents. We looked at a number of different representations for the opponents, but ended up with a fairly simple one at the end of it. We essentially have 7 slots in front of Sophy, 7 slots behind Sophy. We order each of the cars on the track by their distance from Sophy, and then we put them into these slots. We put in their relative position, velocity, and acceleration. And then all of that gets fed then into our network. So this will be my second call out here, which is just that reward design is hard. In reinforcement learning, I'm going to say that there are 2 categories of rewards. One are the true rewards. These are the things that measure the thing we really care about. They're part of the problem definition. And then on the other hand, we have auxiliary rewards. And these are part of the solution. These are things that the engineer can play around with to try and improve the learning process, to guide that process, or maybe they're stand-ins for when the true rewards are unavailable, some sort of proxy. Now, our objective with GT was to beat the humans in a 4v4 race. And not just any humans, but a specific set of humans who drive a certain way and that kind of thing. So how did we encode that as reward function? First thing we need is for Sophy to drive around the track really fast and do so and to stay in bounds. Okay, so we have this progress along the course reward, which is between each observation. We measure how much distance how much progress it's made along the center line. That, of course, is an auxiliary reward. Next, we have an off-course penalty. So if Sophy puts more than 2 tires out of bounds, then that's considered a penalty. This could occur, we might use this to keep Sophy from trying to cut corners, or just help it stay in on the track. It might also be useful if Sophy has an accident, ends up off course, kind of encouraging Sophy to get back on the course. This is actually an auxiliary reward yet again. Okay, so the next one is wall hit penalty. So obviously hitting the wall is detrimental to Sophy's behavior. There actually are tracks where Sophy, without this, Sophy learned that the best policy was to just ride the rails all along the walls. But this, again, is another auxiliary reward. Then we have a tire slip penalty, which penalizes tire slip. And the reason it's there is to improve stability, to encourage stability in the racing behavior. This is yet another auxiliary reward. Okay, so that's enough to get us to go around the track really, really fast and stay in the lines. The next thing that we need to do is to make sure that Sophy plays nice with other cars and is competitive. And this will be a small rant, is that in this scenario in racing, the idea of sportsmanship isn't well defined. There's no one at any point could hand us a clear description of what it meant to have sportsmanship-like behavior. No one could give us a function, a quantitative description of this behavior. And in actual events, what happens is that you'll have a judge or a panel of judges who will watch the race. When there's an event that occurs, such as collisions or going off course, then the judges will review that, look at the video footage, and make a decision about whether or not they think it warrants a penalty. Okay, and that penalty might come seconds to minutes later after the event actually happened. So in our case, then we had to go back and we had to come up with a set of proxy rewards. The first was a passing reward to encourage passing. So as Sophy gets close to another car, it starts to get a penalty for making progress on that car, and then gets a bonus reward for passing that car. It's also penalized for being passed. Yet another auxiliary reward. And the next thing was a series of collision penalties, where we tried to capture behaviors or prevent behaviors that were problematic, considered unsportsmanlike. And this was really a very manual, iterative process that we would come up with some sort of penalty, we'd apply it, we'd look at the performance, and we'd identify situations where Sophy had what we'd consider bad sportsmanship, then try to write a reward function that prevented that behavior. And this is yet another auxiliary reward. So as I mentioned, this was a very manual process of kind of designing these rewards, tuning these rewards. Just to kind of highlight some of the difficulty here, I'm going to show you two clips. First is from an aggressive agent during the
Cockman. These guys need to be working together really in this stage, because
Sophy
look at our
goes ahead and
really
knocks
close up to
out
the back. Was there a bit of contact into the left-hander? I think there was.
Considered too aggressive. Okay. Second case is we have a timid agent
coming towards Indianapolis, so it's the Sophy AI system ahead of Tomoaki Yamanaka. So it's Miyazono from AI, from Yamanaka from AI, from Cockman from AI, from Brian from AI. So it is very, very interesting, and this is proving to be a very exciting climax to the race. And it's going to make things very interesting in terms of the overall point standings then here as well. We come through our nage. That was the last real overtaking opportunity then for Sophy Orange. But is Yamanaka going to try and invent something down into the Porsche?
The reason why in this case that it succeeds in making this pass is that Sophy actually let up on the throttle. When we went back and looked, we can see that Sophy let up on the throttle, assuming that the reason being was to avoid a collision. And I should say at this point, its lap times are much, much faster than the humans. So there's no real reason why the humans should necessarily be able to easily catch up and overtake. Kind of my third rant here is that cherry picking models can be totally fine, even though this isn't how I did things during grad school. So in grad school, when you're publishing papers, typically what you have is you're doing some comparison between algorithms, and you're trying to show that one algorithm maybe is better than another, maybe has lower variance than another. And so you're really doing this ideally doing a very statistical comparison. In our case, we actually had a different objective, which is to identify a particular save point of model that had the features or the behaviors that we were looking for in an agent. Okay. So let me back up and put all those pieces together for a second. So I started out by saying that it was really important that when we have an agent, we're training an RL agent, that we train it against the true reward, the thing we actually care about. And then I went on to describe all of our rewards that we had and how we didn't have actually any access to any of the true rewards in this situation. So what we ended up with is a very manual process for trying to select these agents, these policies that we would send to race against the humans. And I'll walk you through the system a little bit here. So for each policy that we trained, indicated by these rows, we would select, or we would save model clocks at different intervals, indicated by these triangles. Those would go through a set of filters, and we would be left with a handful of policies that made it through the filters. And then we would put these policies through what we call the N-athlon. This is a series of hand-designed test scenarios to go out and evaluate certain skills and behaviors that we were looking for in the policies. Based on those results, we would get additional metrics, and that would all be spit out into a spreadsheet and kind of ranked. As a team then, us humans would sit down, we would go through that spreadsheet, we would look through videos, and we would try to make decisions about what we thought were the best policies. It wasn't always based just on the best scores, but sometimes we'd select policies that were trained maybe under a certain way or a certain method that we wanted to evaluate against the others as a baseline. We would then take this handful of policies and we put them in what we call the policy versus policy scenario, where this was a 4 versus 4 race, just like we were going to do with the humans, that was scored in the same way. We would run them then in this scenario. That would give us a ranking for them, and we would take then the top 2 or 3. We would give them to human testers who would evaluate their performance and say whether or not they liked it, and eventually select the policy that we would take to competition. Okay, now a real key to making all of this work is ensuring that GT Sophy was trained with the right data at the right time in the right proportion. What does this mean? GT Sophy really likes to memorize. GT Sophy does not like out of distribution data. So this means that we had to really try and design scenarios to make sure that Sophy saw a wide range of training experiences that would capture the variety of experiences that we would expect it to see during the race. These are some examples. So we would have situations where we would look at different groupings of Sophy with different numbers of opponents from what we call 1v0. So this is just learn to go out and drive really fast, all the way up to 1v7. So Sophy versus 7 opponents. We would also target particular training scenarios, such as grid starts, where the agent starts in a grid formation, starting from rest. Another skill that we would target would be slipstream, which I will describe in another slide. And then we would also be able to target specific sections of the track, maybe where we noticed that Sophy was not behaving well. Given all of these different training scenarios, we would then take each and we put it into its own replay buffer. So this was not all mixed in. And then when our training agent, our training process was sampling data, it would sample from all of these different replay buffers in a certain proportion, ensuring that the batch that went in for training covered a wide range of scenarios and had kind of samples from all the different scenarios we could imagine being useful for Sophy, and also helping kind of to avoid some of the catastrophic forgetting issues that can come in during training. So I've talked a little bit about slipstream, or I mentioned it. Slipstream is an actual physical effect where you have one car in front of the other, and the front car essentially creates a vacuum behind it. When we put another car in behind that, in that vacuum, the following car can use that to accelerate itself and gain speed and essentially use this as a technique to get to make passes. I'm going to show you one example where Sophy learns something called a crossover maneuver here. So it's in the slipstream, making lots of progress. And then it ends up being able to use that to make this pass on the inside of that corner. Okay, again, I had said that it's important that Sophy saw a wide range of things. One of the things it needs to see was a range of opponents. Okay, so again, our target was these top humans. 4 of these top humans, we didn't have access to that data. We didn't have access to any human data, actually. But what we did have was a built-in AI that's already in the game. That kind of had to stand in as a substitute, even though it's certainly not really the distribution. I should say too, Sophy does not explicitly do any opponent modeling. So anything it learns about opponents is essentially captured as kind of a mean behavior, an average behavior over opponents it sees. So coming back to this, we had built-in AI that we could work with. We had some self-play, so we used Sophy policies as we were training. We would use a selection of randomly selected older policies to play against. We would have things like hand-coded line followers. So in order to get something like that slipstream behavior, we had to make sure that Sophy saw opportunities for that slipstream to occur, so we could set up hand-coded agents to produce that effect. All right, so that's kind of the what. And the next thing I'm going to show you is kind of the response from the drivers. This is one of the drivers, Emily Jones, who was involved in time trial evaluations, trying to beat Sophy's lap times. The short answer is that the drivers actually really liked Sophy and learned a lot from watching Sophy do things that maybe were counterintuitive or not what they were expecting.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learnt a lot about the lines and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI, and I was like, oh, okay, cool, I should do that instead.
Okay, so that's taken us through the development of Sophy, these events where we raced against the top humans, and the Nature publication. Since then, we've been working on getting Sophy into the game in a way that's fun for everyone. Okay, so this is our new objective: make a racing agent that is fun for everyone. And one thing you could imagine doing is doing some sort of optimization over some metric related to human fun. Like maybe how much time people are spending playing the game. That is not something we're doing. We are not optimizing over user metrics like that. Instead, what we are doing is working very closely with the game studio to try and produce human-like behavior and to provide different levels of competitiveness. We've had some practical challenges along the way. The Sophy policy must run on the PlayStation 5. There's not a lot of space left for us. Once the game runs on there, there's not a lot of compute space left for us. So our policies have to be small and they have to be fast enough to run in real time. We also have a bit of a problem of shifting dynamics. So when there's an update made for the game, there is a chance that the physics has changed in some way. It might be small, but what the impact is that the policies that we've trained are not necessarily valid anymore. It's also just been really difficult converting this new objective to reward functions. And there's been many times where we've, as Sony AI, thought about what we think would produce the kind of behavior that the game studio is looking for. We code it up, we build an agent, and then we show it to the game studio, and they're like, that's not it at all. which kind of highlights the next point, which is we are not the game studio and we are not the subject matter experts. So we've really had to shift to working much more closely with the game studio now than we did gearing up for that competition. Practically, we have some long turnaround times. It takes about 2 weeks of training to get Sophy up to production level. And so that means that when we want to make changes to our algorithms, our model, these sorts of things, and see their effect, it can take a long time to see whether or not it had the effect that we were looking for. We also have what I call the burden of success. So we have a whole collection of software behind us that is built up over these last years that we're not eager to change, and we've just incurred a fair bit of technical debt there that comes with any software project. Practically, what has changed since the Nature paper? Well, our policies are no longer single car and single tire. The network architecture allows us to provide information about the cars, such as their mass, horsepower, and engine type, and this allows us to run many different cars, over 400 cars, from a single network. I just want to clarify that point. It doesn't mean at the same time, not 400 cars at the same time, but 400 different cars can all be run from that same network. Players can also enjoy races with up to 19 Sophy-controlled cars. This actually did require some work on our side to get stability. You can get these kind of positive feedback loops sometimes with the agents as they learn when they're on the course with themselves. And so we had to kind of address some of that. We've also had to work at making the game fun for the different humans, not just super fast. And this is, again, this is a different objective. We don't know what fun is for each human. So instead, what we've done is provide Sophy different levels of Sophy and allowed the humans to choose the level that they felt was appropriate for them or that they enjoy playing against. Okay. How do people like the game? They really like it, actually. They really like playing with GT Sophy. GT Sophy can do something that they've never seen in other games, and they certainly didn't see from the built-in AI in Gran Turismo, which is that it can give them a real competitive race and that they can learn from it. So as of today, we are continuing to expand things with GT Sophy, but players can play with Sophy on up to 13 tracks, including Nürburgring, which is one of the hardest in the game. And it is really this massive track. It takes about 8.5 minutes to go around the whole thing. And it's got lots of turns, very difficult. GT Sophy can drive over 400 cars. And we've actually dialed down one of the things we've done too is to dial down, we've made the bounds more restrictive, the penalty for going out of bounds. We still have some upcoming challenges. There's a lot of parts of this game that we're just not addressing at this time. As I mentioned, this is a high fidelity simulator. They simulate things like weather and accumulation of rubber on the track. And those are things we've just not addressed at all. Sophy doesn't shift. It can't drive a manual transmission at this time. There's things like pit strategy and tire wear that are more strategic, high-level things. As I mentioned, Sophy doesn't do any opponent modeling. And one of the things we're really interested in is training an agent that can drive with style. I'll show you this really cool video where we have given Sophy a reward for tire slip. All right, and as I'm nearing the end, I'll just show you some recent work we had published at Reinforcement Learning Conference this summer. This is on using vision-based Sophy. I was not part of this work. This is my colleague's work. But so one thing is, why use vision? So as we look at generalizing our approach to developing agents for different video games, right now we have a special API with GT, but what are ways we can generalize it? One way would be if we can interact with the game the same way that humans do. And one of those modalities is vision. So we've been looking at vision and getting Sophy to drive from that. In this particular paper, Sophy takes screen images as its input, and it also has access to proprioceptive features. It does not have access to these course points like I showed you earlier. It does not have access to information about the relative locations and information about the other agents or other opponents on the track. To get training to work for this, they use an asymmetric architecture. So for the critic, the inputs are this proprioceptive information I mentioned, as well as this kind of privileged information, such as information about the other cars and course points. That's used to train our Q function. But the policy itself only gets proprioceptive information and the image data. And this was sufficient to get us to the point where we could have, in the time trial setting, have an agent that could go really, really fast and get times that were competitive with the Nature paper. Right, before we head into question time, I'm going to head off some of those questions by addressing ones that kind of come up repeatedly in these talks. One, can this be applied to autonomous driving? So the short answer is yes. We have some serious advantages, obviously, by doing things in simulation. We can crash Sophy a million times without any consequence. We can run things in parallel, many, many Sophys at a time doing training. We don't have to deal with sensor noise or sensors failing or any of that. And we don't have to worry about deploying an agent directly on a car either. So yes, we could do that for sure. There's no reason that these techniques that we developed here couldn't be applied. It would still be a significant amount of effort to get this to be transferred over to that setting. Number two, why use quantile regression SAC over regular SAC? As I mentioned, this really comes down to just an empirical thing. There had been work at that time showing quantile regression, reinforcement learning algorithms could produce better results. When we tried it in our case, we saw that as well, and so we used it. I will say that for this rule has not held as we've developed GT Sophy. Often we'll find papers that seem promising and we apply it to Sophy and we don't see the expected improvement that we had hoped for. Could you use planning or a model-based approach? So again, the answer is yes, but. So we have tried MPC methods, model predictive control methods with Sophy. They have not been as effective as our current approach here. The current kind of go-to technique for autonomous racing cars that I'm aware of is model predictive control, which is a planning method. We could also look at model-based training for Sophy. There's really no reason we couldn't. The one caveat is that whatever we come up with, whatever policy we come up with, has to be able to run on the PlayStation 5 in a fairly small amount of memory and to run in real time. Okay. Why don't you use screen images? So I showed you some results where we are researching screen images. And while it would be a nice generic interface for games in general, there is a bit of a reality here that we can't run vision-based training on the PlayStation 5 directly, just due to compute constraints. Number 5, why not learn from human demonstrations? One, we weren't allowed. We just were not given permission to access human data. And two, human data that we could have gotten just wasn't broad enough, didn't cover enough scenarios that we needed, didn't allow us to do kind of the parallelization that we were able to do with our cloud infrastructure. 6, does the agent exhibit the same behavior each lap? Our model is deterministic, so if it gets the same input, it will produce the same output. That being said, the likelihood of seeing exactly the same input is fairly low. That said, we certainly do observe that as Sophy takes laps, there are some consistent behaviors lap to lap. What were some of the biggest challenges with deployment? I've mentioned a number already. One of the ones I haven't mentioned is we needed to convert from Python to C++, and we needed to convert from TensorFlow models to Nabla. Nabla is Sony's own deep learning framework that is deployable on the PlayStation 5. And number 8, is Sony AI working on other games as well? The answer is yes, but that's all I can tell you. So again, just thank all my colleagues who are part of this work. And I'll open it up for questions now. I'm going to make this preface. This is a commercial product and it's under active development, and I am limited in what I can say and will err on the side of caution. Thank you very much. Take questions. I'm not sure how that question series session works here.
Thank you, Craig. That was awesome. I will now ask you all of the secret corporate secrets about how you chain together all of those computers, et cetera, et cetera. I won't. Actually, what I'm going to do is to field the Q&A. So folks that are listening, please feel free to drop a comment in the webinar chat. So just go to your chat window. There's a little box there. You can put that in there. There's Q&A. Perfect. Someone's in the Q&A. So Craig, my job, as Jonathan told me to do, was to read out the Q&A to you. So Michael Mori asks, great talk on GT Sophy. How exactly do you craft the relative magnitudes of the rewards? And is it just a lot of trial and error and domain expertise? Question 2, I saw postings for Sophy AI internships in Tokyo. Does the team there converse in a mix of Japanese and English?
All right, great questions. So the first one is, yes, this is a lot of trial and error. This is a lot of tweaking knobs and comparing results to see if the performance we hoped for came about. I would love a more automatic method. We don't have one right now. Second question is with respect to internships. Sony AI is primarily English speaking. Even here in Tokyo, I live in Tokyo and work in Tokyo. So one of the problems that we actually have is that we have even here in Tokyo, have a really hard time hiring Japanese people because the English part of it is scary.
Any more questions?
This is Jonathan. I'll pull rank and just ask a question verbally. And that, going through your talk, it's pretty clear that there's humans in the loop, literally the entire process.
Yeah.
And as much as we'd like to think that AI is doing a lot of automation, it only gets us so far, and the humans are still in the loop to do that fine tuning, get the insights, fix the bugs, modify the reward functions, etc. So how close are we along the path towards having something like this that literally can learn all of this on its own?
Great question. That's actually a question I'm really interested in, and I'll be looking at some of that with an intern coming up, hopefully here in the next year. I think that as much as you can criticize LLMs and things for all of the ways that they are maybe don't have the right objective function, don't do this or that, I think they do provide a real interesting opportunity in terms of the interface. And I think there are ways that we can leverage LLMs and related technologies to automate some of what we do still. There are some really good works or interesting works on using LLM-based systems for reward design and for evaluation. And one of the ways that they kind of excel, I'm hoping, is in capturing some of the vagaries of the feedback that we get from, say the game developers, and converting these things into reward function. That said, one of the ones to me that still seems like a lot of work is the feature design. I don't know how to get around that, where we talk about end-to-end training, and the reality is that that pipeline of what goes into your network is still so key in making sure that your agent can properly generalize and can learn well. And I feel like that one's still quite a ways away.
I see no other questions, so I'm also going to jump in with a verbal question, Craig. This is all very, very cool, and like you can imagine, we get a lot of our conventions. Oh, there is another question. I'll ask my question quickly then. So we as humans build conventions in like the race pub after the racing event or whatever racers do after. LMs aside, though, do you think the emergent conventions of racing, if you were just to give agents their druthers and let them build their own emergent conventions, do you think you'd see structured conventions like, hey, don't cut people off and those kind of things, don't run people off the road? Or do you think it would just be like you just see optimization behavior without some of that latent structure in terms of behavior policies?
Are you suggesting that you let the agents essentially build emergent racing behavior?
Maybe that there might be nice structure there when you did. I don't know.
I think obviously there has to be something in there that guides it. Something. What are you optimizing over? You need something to optimize over. And if for an agent to experience something that would be fun, that would necessitate something like good behavior, good sportsmanship behavior, there needs to be some goal that kind of conditions that. So yeah, I think definitely it's still up to us humans to largely say, here's the thing that we care about at the end of the day. Go learn something that does that. So I think we're still in that category for sure.
Cool. All right, we have two more questions rolling in here. One is Hayden Steingrimson. I hope I said the first name and last name correctly. Craig, can you please discuss your view on superhuman performance in the second Sophy human competitive event? Sophy won. Does that mean that Sophy has superhuman performance? Would Sophy need to have the same processing delay in perceiving different metrics as a human has for superhuman concept to be valid? Related question, enjoyable for everyone. Seems that being able to win plays a big role. What else matters and does not matter? How the human wins. Sorry, I messed up the question. I apologize, Hayden.
Yeah. So this is a great question. It kind of hits on some of what the reviewers originally commented on too, which is, how human-like is Sophy? Is it fair? Is it a fair comparison? I'm going to push back on that one a little bit and say that I don't think that was ever the goal. To build Sophy that solved the game in the same way that humans did. We certainly, I would say that Sophy is superhuman, or different models of Sophy, they're not all the same, do achieve superhuman performance. That means they have, better lap times, better overall strategies for passing. And there's some additional things. They are able to do this consistently. Those lap times, Sophy never gets tired. Sophy, never loses focus. Certainly putting some of those things in there might make Sophy more human-like, but it's certainly in terms of that initial competition, that was not the goal. It was really to see how far we could push this and could we achieve an agent that was better than human. And that means taking advantage of the things that computers and algorithms can do that humans can't do. Now, if your goal, of course, is human-like behavior and a human, to learn in the same way as a human, then that's a different problem setting.
And this seems relevant as well to like the action per second in the microservering and AlphaStar, where there was questions about like the burstiness of the actions per second and whether that was comparable to a human or not. And this actually leads to the next question here from Charles Robertson, Craig, which says, you put special training features such as followers for Slipstream. How about Sophy inventing techniques and possibly inventing something completely new, even to humans, on this sort of innovation theme and innovation front?
Yeah, so there's This is limited by the physics. There's only so many things in there. Slipstream is something that comes up because of the reality of physics as an opportunity. What we did see, though, is that there are kind of traditional approaches to racing. Like, these are the rules of thumb about how you should take a particular corner. And what we see once we optimize Sophy is that in many cases, Sophy doesn't follow those rules of thumb and instead ends up taking lines through the corners that are completely at odds with what would be the traditional approach. And those, interestingly, the professional drivers were really interested in those because they were opportunities to learn something that hadn't been seen before. In terms of other strategies, I'm not really sure I've seen anything kind of emergent there.
All right. Any other questions from the audience?
I think Jaap raised his hand. I will allow him to talk.
Okay.
Jaap, go ahead. Oh, you're still muted though, if you're there.
Is this now understandable?
Yeah. Yes.
Okay. Yes. I listened with much pleasure and with much, I would say, interest, because I think what will be the next step. So in the car, driving the car, and we have recently this weekend we had a world champion, as you know, for fast racing. Yes, and this is another technique than the technique we had here. But anyway, the research can be widened. I'm absolutely sure, and that would be great. But anyway, what is the end? We know that from what I said and what was mentioned here also from the games which we developed, and there we can see no end also, but it takes a long way. But with driving cars, because then we have driving cars, driving airplanes, driving, I would say, and then we go to military, and then we see that we have now not a big future, but a wide future of an unimaginable future at the moment. So I would like to have your opinion about, I would say, these developments.
So can you just summarize what your question is? Kind of, where's the end to AI application in society? Did I understand that correctly?
That is the most wide, I would say, formulation of my question. That's absolutely true. But I'm already happy with some branches. If you say some branches, I would say growing branches out of your research, that would be fantastic.
Okay. In terms of things, say with vehicle control, I think there still are lots of opportunities for automation. Things like train control, boat. We're seeing boats being controlled now, as you mentioned, planes, obviously. So I think there certainly is a lot of opportunity in that space to kind of fill the things. There's always going to be, of course, this trade-off between that we're going to make as this decision making that we make as a society about what level of automation we are comfortable completely handing over and what level we want a human for. I'll give you an example. One of the trains I take here in Tokyo has no conductor on board. I don't know that it's automated, but they always make this announcement that there's no conductor on board, which is a little bit, it can be a little bit surprising or unnerving.
Now that could be the first step of the further development, that we probably have no conductors anymore necessary for, I would say, for guiding us. And then, of course, then we have a split world, the world of computers and the world of human beings. And in my opinion, but that's, I would say, there's a particular idea. I think that in the longer run, the computers will outclass us in intelligence on all areas.
Yeah, I think that's a bigger question for society and economics, and I would suggest that we need to consider kind of some of our economic structures and the motivations we place on profit over people.
I fully agree with you, and I'm happy with the answer. But that was, I would say, what you say in the beginning when I started to formulate my question. That you ask yourself, where are you going to? And now you have the end goal, so to speak, of one of the end goals. You say, oh, that's too far. And also here, I agree with you. So the only thing is that we now try to make it, I would say, to have it in the discussion, and that's already, I would say, satisfying for me sufficiently.
Yeah, this is a great conversation, maybe over a beer.
Yeah, no, thank you for first of all for your very interesting, I would say, statements and for the enthusiasm with which you presented your research. So I was happy to listen to you.
Thank you.
Okay, we have one more question. I think we will wrap it up. We're right in time, I think. So this is turning out nicely. Hayden has another question. What surprised you the most? What game states that needed attention were least expected?
In terms of what surprised us was that initial event where we had built, as I said, we had this expectation that every car out there would drive to everyone out there would drive to the best of their own ability and try to maximize their own reward as it was. And to be just kind of confronted with the humans behaving in this way we didn't expect, which in hindsight seems so obvious. That was the most shocking thing I think we experienced, or that I experienced personally, was just how blindsided we were by something that seemed so obvious in hindsight. Yeah.
All right. Well, I think we should wrap right on time, unless there's one last minute question coming in. I'm gonna do the auction thing, going once, going twice. Nothing coming in. All right. Well, domo arigatou gozaimasu. No, domo arigatou gozaimashita, I think we should say. Better, right? Is that right? Is it better, Craig? See, this is why.
Yeah, that's great.
I'm not moving Tokyo either. Thank you so much, Craig. This was a lovely talk. As everyone said, there's been great feedback, and I think the questions showed that you really pulled out some interesting themes and gave everyone in this community something really sort of vibrant to talk about. So thank you again for that lovely talk and all of the content you shared with everyone here today. Thank you, Craig.
Okay, thank you so much.
Yeah, thank you, Patrick, for sharing, and thanks a lot, Craig, for this wonderful talk.